Hi. One of the things that I discussed in the last lecture is that Dijkstra's algorithm doesn't work when you have edges with negative weights. So now we're going to learn about the Bellman-Ford algorithm, and this is a single source shortest path algorithm just like Dijkstra. So it finds the shortest path from one vertex to all other vertices. But the difference is this algorithm will still work if you got a graph with edges with a negative weights. So because it does more than Dijkstra in a way, it's actually worse than Dijkstra in terms of complexity. The complexity of Bellman-Ford is big O phi times E, while Dijkstra is, well, you can do it in phi log phi plus E, I guess. We're going to go back to this later after we discuss the algorithm. And apart from that, we're just going to use the same definition for the graph. We're going to set S to be the deciding vertex. And we're just going to jump right into an example of the algorithm, because it really is a very simple algorithm. You don't have to be scared about it. You'll see. And also, we're going to assume that the graph does not have a negative weight cycle, because if that's the case, then there's nothing we can do about it. We won't be able to find the shortest path. Okay, I think that's pretty much all I need to talk about before we go into the algorithm. Just one definition. We're going to say that delta V is the weight of the shortest path from S to V. Just a nice notation to make it simpler. And yep, let's jump into the algorithm. Here is the algorithm, and as you can see, it's pretty short. So I separate the algorithm into two parts, the blue part up top and the white part, because I don't want you to worry about the white part yet. We'll get back to it later. It will make sense why it's there. So for now, just look at the three lines here with the blue part. Now, only three lines, and the first one is actually just setting up, because you're setting the shortest path to S to be 0 and everything else to be infinity, which is exactly how you do it with Dijkstra. This is how you start with Dijkstra as well, right? So really, there are only two lines of concern here, the two for loops. Now, the first for loop, it goes phi minus 1 times, so just the number of vertices minus 1. And the inner loop, for basically for each iteration of the outer loop, you will go through every single edge, and then you relax it. So hopefully you remember what relaxing means. It just means that you try to use an edge to see if you can improve the shortest path that you have so far. So basically, let's say I can go from S to A at a cost of 20. I can go from S to B at a cost of 5. I can relax the edge BA. If, let's say, BA costs only 5, then now I can go from S to A at a cost of 10. That's what relaxing means. Just seeing if you can use the edge to make your path shorter. I'm also not sure if I should use the word relax or try to relax. I think trying is implicit in relax, but I've heard people say both things. But don't worry about it. If you say relax, I know what it means. And that's really it. It's a very simple algorithm. It'll look even simpler once we do an example. So that's what we're gonna do now. So here's a graph with two negative edges, SE and DC. So SE costs minus 4, DC costs minus 5. And let's try to find the shortest path from S to every other vertices. I'm going to have a table here that tells you the shortest path that we have so far. So right now it's infinity for everything. You can also see the shortest path here, like in these blue infinity symbols here. What else? Well, these are the edges. And this is the order that I'm going to go through the edges. Now, for each iteration, you will have to go through all the edges. The thing about this algorithm is the order that you go through the edges must be the same all the time. Well, you would write the code like this anyway, right? You will go through the edges, and there will be a set way that you go through the edges. So this will be automatic anyway when you write the code. But that's pretty much all the setup we need. We have the edges. Let's go through them one by one and try to relax the edges. All right, the first one is SE. Right now, it costs infinity to go to E. Well, it costs infinity to go to everywhere. So Can I use the edge SE to make it better? Sure, I can, because then now it only costs -4 to go to E. Next up is SB. It costs 8 to go to SB. Sorry, to go from S to B. So now the shortest path to B is also 8. Next one is BE. And will that help us in any way? Well, it costs 3 to go from B to E. And it costs 8 to go from S to B. So if I go SBE, it will cost me 11. But I can already go to E at a cost of -4. So who cares about like SBE? It's not going to do anything. Next up, BD. It costs 9 to go from B to D. And well, it costs 8 to go from S to B. So now it will cost 17 to go from S to D. Next up, CB. Well, I can't go to C anyway, so it costs infinity. So I'm not going to do anything. It's not going to make any change. Next up is DC. It costs -5 to go from D to C. So at least I know I can go to C now. And it cost me 17 to go to D. So how much will it cost me to get to C? 17 minus 5, 12. Finally, ED. It costs 1 to go from E to D, and it costs -4 to go from S to E. So, how much will it cost to get to D? It will cost -4 plus 1, it will just cost -3. And that is better than the 17 that we have right now. So, we will replace 17 with -3. Are we done? No, because you can easily see in the graph here that it costs a lot less to get to C than 12. You see that it costs -3 to get to D, and it costs -5 to get to C from D. So it really only costs us -8 to get from S to C. And you don't see that here, right? Because the in order to get -8, we would have to relax SE, followed by ED, followed by DC. But the order that we did the relaxation is the other way around, because we did SE, followed by DC, followed by ED. So that's why we still have it at 12. And this is why we're going to be doing this iteration again. Now, again, the important thing is that in the next iteration, the order that you choose the edges must remain the same. Otherwise, this algorithm will not work. By the way, you kind of see why the order matters before anyway. When we were doing, let's say when you pick BD, right? When you try to relax BD, we set the distance to D to be 17. But after that, we check ED, and we know that we can now go to D just -3. So imagine if you do the, if you relax these two edges the other way around. So if you check ED first and then you check BD. Well, here, if you check ED up here, then you will set it to be -3. So when you try to relax BD, it doesn't make any difference. But imagine further if you try to do both before you relax SE. So let's say you do SE last. If you do that, by the time you check ED, you don't even know if you can get to E, right? Because E will still be infinity. So in that case, ED will not do anything at all. So just get used to this, like get used to the idea of like path relaxation, and know why doing the relaxation in a different order will matter, because that's the main crux of this algorithm. Okay. So right now we are done with the first iteration. We're going to do this again, right? Let's keep on going. And this time I'm just going to do it a lot faster now. I'm just going to list everything, because you can check this yourself. Most of these relaxations will not make any difference. Only one will make a difference, and that's your DC, which we discussed before. That instead of like 12, it should only cost -8. I'll leave it to you to confirm for yourself, but you can quickly see it anyway. BE, well, we did that before. It wouldn't make any difference before, so it doesn't make a difference now. BD, well, we already used it before. CB, well, this would actually make a difference if we know we can get to C at -8. So see again, this is where the order matters, because it costs you 7 to go from C to B, and before we had C equal to 12, right? At that point, we still have the cost going to C to be 12. So if I just add 12 to 7, I'm going to get 19, which is way worse than 8 that we have so far. But now that we know that it costs only -8 to get to C, you can get to B at a cost of 1. Sorry, -1 actually, right? And that's what's going to happen in the next iteration. So at this point here, at that point when you try to relax CB, it costs you -8 to get to C. So just add 7 to it to get to B, it'll cost you -1. And you keep on doing this. We've done 3 iterations. We have to do 4 iterations because you got 5 vertices in the graph. Do I have it? Actually, no. Because if you do one more time, you can check it yourself. If you do one more time, there will be no more changes. This is really it. That's all there is. Yeah, you can double check yourself. But the next iteration pretty much gonna say no change, no change, no change, no change all the way through. So that's it. That's the algorithm. And hopefully you can see that it's pretty simple. Now, on the correctness of the algorithm, if you want a formal proof of correctness, then you can read it in CLRS, because if I go through it, we got to be here for another hour. And the way I see it is that with this course, you should know how to prove the basic things. That's why we went through loop invariance and proof by induction. But when it comes to specific algorithms like this, I don't think you will get much value by going through the formal proof. Don't get me wrong, I think it's good if you can do these kind of things, but this is more geared towards students who are interested in research or in mathematics. So you can definitely read on your own, but for the majority of you, I think just having an intuition on why this works is more beneficial. Because who knows, you might be able to apply the same approach when you're designing your own algorithm or something. And that is a key thing in my opinion, because if you have a confidence that you're running an algorithm that's correct because it's based on something else, I think that's great. So I'm just going to give you my intuition for it, and hopefully you already kind of see the same thing. Let's just say you have 4 vertices and 4 edges in a graph, and these are the 4 edges. So sorry, this is 4 and 4. I guess it gets a bit confusing. I should have more than 4 edges, but 1, 2, 3, 4 are the edges, and these are the 3 iterations, because v is equal to 4, like there are only 4 vertices, so I only have to go through 3 iterations, and in each iteration I go through all the edges, and I always go through the edges in the same order: 1, 2, 3, 4, 1, 2, 3, 4, 1, 2, 3, 4. Now, what is our goal? Our goal is to find the shortest path from one of the vertices to every other vertices. So, think about this. Did you try the path using the edges 1, 2, 3? So don't worry about which edge is connected to which vertex. Don't worry about the details. Just look at the list of edges and ask yourself, there are edges 1, 2, 3. Did I use that edge? Did I go from 1 to 2 to 3? The answer is yes, because you, at least in the first iteration, I relax 1, and then I relax 2, and then I relax 3, which is the same as me going from 1, using edge 1, and then using edge 2, and then using edge 3. Did you try the path using the edges 1, 2, and 4? The answer is again yes, you did. It's also captured in the first iteration. Did you try the path using the edges 4, 3, and 1? Yes, you did. Why? Because in the first iteration, you tried to relax the edge 4, and then in the next iteration you try to relax edge 3. So you do this after you relax edge 4, and then in the final iteration you try to relax edge 1, 4, 3, 1. So can you try to convince yourself that you try every combination of 3 edges? Actually, like, did we do 4, 3, 2, 1? No, we didn't. We never tried to relax edge 4, edge 3, and edge 2, and edge 1. Well, the best we did was 4, 3, and 2. Once we've done that 2, we never tried to relax at 1 again. Oh, so we don't have this combination. But does it matter? Think about the path using edges 4, 3, 2, and 1. You have a graph with 4 vertices. If you got a graph with 4 vertices, the shortest path between any vertex, any 2 vertices, should just be of length 3. If you have a path of length 4, that means you have some sort of cycle going on, which is not the shortest path. Remember that in the previous lecture, we discussed how the shortest path should not have any cycle in it. And so if we do the loop 3 times, that should give you the shortest path, because that's the maximum length of the shortest path, because you only have 4 edges. So effectively, we tried every single permutation of length 3 in the algorithm. But wait, would that cause e factorial then? Well, no, because of how we structured the algorithm. It's like every permutation is contained if we do the iteration many times with the same ordering of the relaxation. This is what I find cool about the algorithm, and I have applied the same logic more than once in completely different problems. Like I just have a loop that does the same thing again and again, and I know that I captured the permutation. Right, so that's it. That's my intuition on why the algorithm is correct, which to me is like a nice tool to have. And yeah, I guess let's go back to the algorithm again. You know what this blue bit is doing now, and you know why you only need to do it v minus 1 times. Okay, pretty much that's what we discussed just then. And now, what about the white bits? What about this stuff in the bottom here? This code is here to test whether or not the graph has a cycle with negative weights. So as we discussed before, if you have a graph with a negative weight cycle, the shortest path is not well defined, so we're just going to give up. Now, once you worked out all the shortest path, like from the blue bit here, you try to relax every single edge one more time. And if at any point you're actually successful, you find a shorter path, this signifies that there is a negative weight cycle in the graph somewhere. Because what we said before, right? The shortest path should only be of length phi minus 1 at most. If you can have a path of length phi, and it's actually cheaper than what you had before, that means you have a cycle somewhere in the path. And the cycle actually reduces the shortest path, which means there's a negative weight cycle in the graph somewhere. Okay, so that's what that code is doing. It's just checking to make sure that the algorithm is actually correct, in the sense that this is a graph with no negative weight cycle. Okay, now let's go back to the complexity. We said earlier that the complexity of the algorithms is big O phi times e, and I hope that's obvious because you will go through it phi times, well, phi minus 1 times, and in each iteration you go to all the edges, so that's your times e. And what I want to do now actually is compare Bellman-Ford to Dijkstra, because Dijkstra you can do in v log phi plus e. Now, why is Dijkstra faster? Well, it's just in terms of complexity. We know that Dijkstra is faster because it doesn't have to worry about negative weights. But Dijkstra is faster here because when you look at the number of edges compared to the number of vertices, then the number of edges is bounded above by the number of vertices, but you can have up to phi squared edges in a graph with phi vertices. Right? Think about it. If you have a graph with 5 vertices, if you connect every single one of them, you have around 25, not exactly 25, less than 25 actually, but you will have around 25 edges. So E is big O phi squared, which means I can just replace the E here. In the worst case, well, in the worst scenario, I guess I should not say worst case. In a graph, in the worst scenario, this E can be up to phi squared. So your complexity would be phi cubed, as opposed to Dijkstra, which is just phi log phi plus e. Well, let's say that E here is also phi squared. You will still have big O phi squared here, not phi cubed. So that's why Bellman-Ford is worse. But of course, Bellman-Ford can capture the shortest path when you have negative weights. Don't forget about that. You can improve Bellman-Ford to V plus E if you have a directed acyclic graph. If you have no cycles, but sure, then it can be, you can run this in just V plus E. You can see CLRS of 24.2 if you want to know more. I'm not going to examine you on that. And also, like I said, I'm not going to test you on formal proof of correctness or even the complexity. I guess if you understand this, that should be enough. Just understand why it's VE and understand why Dijkstra is V log V plus E. Actually, maybe Dijkstra, even if you understand this, V squared plus E, that's good enough. Alright, I just need you to understand the basic idea. I'll leave the formal stuff. If you're really interested, you can go dig into the textbook, go read yourself, have fun. It's a great thing to do, actually, if you understand all the math. But for the purpose of an exam in this unit or assignments, you don't have to worry about the formal stuff, right? We'll just do more things instead. Okay, so that's it for Bellman-Ford. I'm gonna go back with two more algorithms, the all pairs shortest path ones, and I'll see you then.